All right, so we're going to start with energy transfer. And for those of you who are following along, we're on review book page 88. And of course, if you don't have a hard copy of your review book, you can look online on Google Classroom and find it. All right, so energy transfer. The way that energy transfers, the same way that heat transfers, you always go from high to low or source to sink. Okay, so when you're talking about that, you're talking about like a high temperature to a low temperature, right? And think about it. When you have a high temperature, right, the molecules are going to move really fast. In a low temperature, they're going to move very slowly. Okay, now, over the summer, let's say you open your front door, right? Inside your house, you have your air conditioning blasting because it's up 90-something degrees, right? At some point in your life, you may have been yelled at or heard the term, close the front door because you're going to let all the cold air out. Yes or no?
Yeah.
Right?
Yeah.
Now,
Yeah.
I would not turn around and say you're wrong because that might get you into some trouble, right? But they're wrong. You're not letting the cold air out. You're letting the hot air in, okay? Again, I don't recommend you turning around saying, well, actually, you're wrong, because then you're going to get in trouble, okay? But because the hot air molecules are moving around a lot more, they're going to rush into the house, and you're going to, like when you open that door, you feel a rush of hot air, right? When you're outside and someone opens the door to you, you don't necessarily feel a rush of cold air. You might, as you walk in, you might, but you're not going to feel like, unless you're standing right in front of the air conditioner, you're not going to necessarily feel a rush of cold air. And the reason is because of how things transfer. So it's always going to be high temperature to low temperature, right? It's going to be from the source to the sink. Okay, so here we go. All right, we have our hot temperature here. Heat is going to flow from hot to cold until eventually it's going to go to equilibrium. Now, equilibrium, we went back. The video clip that is there is actually the one I was telling you about at the beginning of the year, which was the two people throwing apples, and eventually they will be at the same rate, right? But the amount is different. So if you guys really want, I will show you the little video clip real quick. Marshall.
Grammarly does more than catch errors. With Grammarly, you can find... What did you learn?
I learned to oil
Traps the water, and the steam forms... Hi, Kenya.
Oh, hi, Raheem. How are you doing?
I'm fine, and you?
I'm good, thank you.
What are you doing?
I'm just warming up some soup for lunch. Would you like some?
Yes, please.
Okay, let me put the lid back on. I don't want to lose too much water. I don't like thick soup.
What do you mean? How does putting the lid on keep the soup from getting thick? The steam still evaporates.
Well, kind of like what I learned in science today.
Really? What did you learn?
I learned all about dynamic equilibrium.
I don't know what that is. What is that?
Okay, does anybody else notice she's holding onto the pot? What's the problem here if she's holding onto the pot like that?
You get burned. It would burn her hand.
Right. So you see how right here, even if she was just holding onto the handles, it'd be one thing. But this part of her hand, she's kind of like leaning on it. She should be screaming in agony because we know metals are good conductors of heat. And since her hand is colder than the pot should be, right? The hot molecules should be hitting her hand and burning her. Just wanted to point that out.
Dynamic equilibrium. Doesn't equilibrium mean that nothing happens? Objects are at rest.
Well, let me show you with this pot of soup right here. What happens when the water evaporates?
Well, it moves out of the pot and into the air around us.
Okay, I'll put the lid back on. What happens now?
The lid traps the water, and the steam forms droplets on the pot, which moves back down into the pot along the sides.
The water changes from a liquid to a gas, but because the lid is back on, it changes from a gas back to a liquid.
So that's why you put the lid on, because the water in the gas form can't escape, so it changes back into liquid water.
That's right. But remember that because the pot is on the stove and on a high temperature, this means that the water in the soup carries on evaporating to form water in the gas phase.
Does that mean that evaporating and condensation takes place at the same time? It seems like nothing is happening.
You've got it. Overall, it seems like there's no change in the amount of liquid water or water in the gas. There's a state of balance or dynamic equilibrium inside the pot.
I understand why you say there's equilibrium, but what does dynamic mean?
Dynamic tells us that at a microscopic level, water molecules are changing from gas to liquid and liquid to gas all the time, even though it seems like there is no change.
That's really interesting. But enough talk about chemistry. That soup smells really good. Is it time to eat?
Yes, it is. Pass me the bowl and I'll dish up.
Many learners find it hard to understand what it means to have the rate of the forward reaction equal to the rate of the reverse reaction.
This is what I've been telling you guys.
Let's think of the forward reaction as a man throwing apples over his neighbor's wall. At first, only man A throws apples because man B does not have apples to throw. Eventually, man B starts to throw apples back. Think of man B throwing apples back as the reverse reaction. At first, man B is slow at throwing back, but he eventually speeds up. Man A and man B end up throwing apples at the same rate. Can you see that the number of apples on man A's side stays the same, and the number of apples on man B's side stays the same? We say they are in dynamic equilibrium.
Okay, so that was the example that I had given you guys at the beginning of the year, right? So you have one guy who's throwing apples to the other guy. This guy can't do anything. They're not at equilibrium yet. The second they're both throwing at the same rate, that's when they become at equilibrium, okay? So when it comes to this, right, on a very hot day and you get a glass of water and you add ice to it, if you leave that alone, the ice is going to melt until you add enough. You might have to keep adding ice and keep adding ice and keep adding ice until all of the ice and all of the water remains consistent. It remains constant. That's where you have a dynamic equilibrium. In cases like this, right, where you have a hot side and a cold side, eventually the temperature, the hot temperature is going to keep flowing towards the cold, and the cold is going to cool it down until it reaches somewhere in the middle, okay, where both of them are going to be a certain temperature. So if you had like hot boiling water and you added ice to it, eventually the hot boiling water is going to cool down to the point where it's somewhere in between the ice and the water temperature itself. Okay? So there are 3 different ways that we transfer energy. And you guys have been learning this since 7th grade. Okay? I know you have. There's conduction. Conduction is when you have things collide and then the transfer of energy happens. So when you had the molecules inside of the round bottom flask from earlier, and I said they're going to collide with the thermometer, and the more that they collide, the more that it's going to make the alcohol inside the thermometer increase, and that's how you get a higher temperature. Okay, so this is when you have them colliding into each other. So for conduction to happen, you need to touch. Okay, 2 things need to touch each other. Okay, then you have convection. We have been dealing with convection currents all year long. Okay, convection currents has to do with the density. okay? And that's when, if you have a heating source here, right, the molecules here move faster. When they move faster, they spread apart. When they spread apart, they become less dense. When they can become less dense, they rise up. Well, eventually, when you move away from the heat source, right, you move away from the heat source, you get colder. That means the molecule condense more, and they get more dense, and they fall. So they go in a circle, right? And they go up right where the heat source is, okay? That's important that you understand. So where the heat source is, that's where the molecules are going to rise. And then they're going to move away from the heat source and come back. Oops, sorry. Okay? And then radiation is through electromagnetic waves. Okay? So things like from the sun. That's why we have ultraviolet radiation that comes from the sun. The next picture you are going to see, I actually got out of your old 7th grade textbook. Okay? Some of you guys may have had notes online. You have seen this picture a million times. Here's conduction, where they actually have to touch, right? The only way you can conduct heat energy is the hand, and he's probably burning his hand right now, or her hand, okay? They have to touch each other. Convection, notice as from the heat source is down here, it's going away from the heat source, it cools down, it gets more dense, and then it falls back down. It goes in a circle, and just depending on where the heat source is. So the heat source is right here in the middle, right? It goes up, then moves away from the heat source, gets more dense, and falls back down, and it just keeps going. It goes in a circle. They're called convection currents. And radiation would be the fact that there's no touching involved, okay, and it is coming off of the fire. All right, so conduction, first of all, it's going to be best for solids, right? Because you can actually grab the solid, right? Don't do this. Don't try this at home. You will get really burned. Okay, don't play this game. Okay? All right? If you have to use a heating pad on your back, right? That's you had to touch in order to get the heat transfer. For convection, it's gonna work the best for fluids, so things that are in liquid form. Okay? But you can have convection currents for gases as well. Right now, your heat is kicking on a little bit because it's a little cold outside, just a tad. It's about 35 degrees according to my watch. Okay, it's a little cold out. You probably have the heat on somewhere in the 60s. Okay, anytime that the temperature in your house falls below that temperature, your heat's going to kick on. A lot of you guys have steam heat. Steam is a gas, right? That's gaseous water. Okay, what does it do? It heats up the water enough eventually, because you're heating it up into a gas, right? The molecules move further away, which means that they become less dense. The heat will rise up, it moves away from it, it cools down, it falls back down, and comes back. Okay? This is exactly what I was just saying, right? So you have your radiator, the heat source. It always goes up where the heat source is. You'll also notice, except for the newfangled, what are those called? They're the, the mini splits. They are both heating and cooling. Those are a little weird because the warm air wants to stay up top. But a lot of times with the new ductless air conditioners, they're also heaters. Okay, there's one unit for it. It doesn't follow the same rules because it's heating up, unless I'm not sure if it shoots out this way or if it shoots down. If it shoots down, it makes a little bit more sense. Okay, all right. This is everybody's most hated reference table. It's just pretty and colored, right? You have all of these up here. These are all convection currents that are going to come off. And if you look at the equator, that's where the hottest point is, right? So it's going to rise up at the equator, move away from the equator, get more dense, fall down, cool down here, and then go back towards the equator. So these convection currents increase or move up wherever the heating source is, okay? We have a whole bunch of them on the inside of the Earth, too. Okay, that's a volcano right here. Okay. All right. And then radiation. You don't need anything in specific, right? Radiation is just going to be like from fire or from the sun, right? You stand in front of a little fire. If you're making s'mores, you stand in front of the fire, right? And you feel the heat. What you're actually feeling is the radiation coming off of the fire itself. Right? So like the sunlight. Okay? So you guys have homework for tonight in your review book. I'm going to post it in a minute. All right? It'll be review book page 86 to 87, questions 13 to 24. And if you remind me tomorrow, I will start with this video. Oh, maybe not because it doesn't exist. Okay? Does anybody have any questions? All right.